Hello everyone, I'm Bill Su, and thank you all for coming here today, or if you just came here for advisory and not for this. I'm really glad to have you as well. So over the summer, I participated in a 6-week research program known as UC Davis Young Scholars Program, and it's really great. I'll talk about that more towards the end of the presentation, but this is the research I performed during those 6 weeks. Benzyloxycarbonyl, or CBZ tagging, and the enzymatic synthesis of human milk oligosaccharides, or HMOs. So I performed this research under the mentorship of my PI, Dr. Shi Chen, and my graduate students, Zimin Zhang and Yueyuan Bai. So here is some background. What are human milk oligosaccharides, and why do we really care about them? Now, HMOs are the third most common component in human milk, and currently they're not included in any infant formulas, or if they are, like very few infant formulas. One of the big reasons that breastfeeding has such an advantage over infant formulas is because of these human milk oligosaccharides. They provide a number of benefits, so one of the main ones is they're a prebiotic. Essentially, they serve as food for establishing a healthy gut microbiome, and this helps prevent intestinal disease. They can also be an antimicrobial by preventing bacteria from forming biofilms or sticking to each other, and also help brain development as they carry important sialic acid, which is crucial for neurons. So let's get a little bit into the structure. It's important to know HMOs are complex sugars. They're polymers. Basically, they're long sugar chains made up of a bunch of simple sugars. Here you can see the 5. You have galactose, glucose, fucose, glucanash, and U5AC. Another really important thing is all human milk oligosaccharides can be derived enzymatically from lactose. So if you have lactose, you're able to use enzymes to add these sugar groups to it. So on the bottom, you can see this is a sample human milk oligosaccharide, and the red box is basically the lactose. So a lactose, if you didn't know, was lactose plus glucose. This is what my research focused on, benzyloxycarbonyl tagging. So this CBZ group is detectable under UV light, and we like to attach it to the lactose because it makes the reaction much easier to detect, and we can check its progression. Additionally, it's easily removed afterwards, and it just helps make the synthesis and purification a lot easier. So in order to do this and attach a CBZ group to the HMOs, we like to do it at the very beginning and attach it to our lactose. If you remember, all HMOs can be built from lactose. So if we attach it in the beginning, it helps remove a lot of the complications from deciding where to attach it. So this can be really simply made using chemical synthesis. However, the synthesized version is really impure. So there has been past research on HMOs. The first published papers were around 1956. Since then, 100 structures have been identified, and over 200 structures or 200 HMOs have been discovered. So there have been many studies on HMO synthesis, but very few studies actually look into CBZ tagging to improve the purification. So that's the goal of my research, to explore CBZ tagging to improve the synthesis of human milk oligosaccharides, and also to improve the crystallization procedure for our precursor, LacβNHCbz. So let's get really quick into LacβNHCbz synthesis. It's a relatively simple chemical synthesis. All we do is take lactose. You can see we replace the OH group with an NH2 and amine, and then we eventually will react the amine to and add the CBZ group right here. The issue with this is it's very messy, or not messy, but the end product is very dirty. As you can see, it's supposed to be a white powder, so we need to get rid of all the impurities. And that's where crystallization comes in. So we tried, we were actually basically the first people, as far as I know, to test crystallizing LacβNHCbz. We tested 11 different solutions, so basically different solvent mixtures or maybe temperatures, and a bunch of variables. And each test, unless specified on this chart, we use 0.4 grams of the crude material. So if you see here, number 3 is the only solution that actually worked. So solution number 3 was the only one where we could detect any significant amount of LacβNHCbz. We use things like mass spectrometers and TLCs, which can basically just tell us what compound we think should be there. And when we did that, for all the other samples, no LacβNHCbz came up. Additionally, here we have some UHPLC readings. It's just fancy chromatography, essentially. So the single peak on the left indicates high purity. We call it single peak purity. So it's relatively pure. And you can see the units, it goes up to 800 or 700. On the right, we do not see such a peak where we expect at 4.2-ish. it does not exist. So this solution number 8, we know there's almost no detectable LacβNHCbz. So we successively sized it up to larger and larger scales, and every single time we got similar purity results, but we got even better yield results. And so speaking of yield, here's just some really simple calculations. We expected about 6.94 grams, and we got like 20 grams, 19 grams of crude, so it's about 35% LacβNHCbz, our raw material. Like I said, it's very dirty. And so after crystallizing, we got like 25% of the crude's mass back. So theoretically, we can see a yield around 70%, which is actually really good. So crystallization has a lot of benefits compared to the method that the lab and like other people use, because generally using machines such as column chromatography are really expensive. Like these machines can run from $5,000 to $10,000. You need to spend a lot of time to set it up, and all these you have to collect the fractions, and then you have to evaporate them, and then you also have to buy the columns, which cost more money, and then load the columns, and it's so annoying and tedious. Our procedure using crystallization, all you really need is a hot plate and a refrigerator. So if we had that in this classroom, we could actually crystallize it fairly easily, and some solvents. It also forgoes, like I said, it forgoes the need for expensive machinery, and it gives us pure LacβNHCbz than if we just try to precipitate it out. And basically as pure as the column chromatography, as far as we know. So there's still a lot of future goals that we have. Solution number 3 is very promising, but the yield can likely be improved by tweaking the crystallization parameters. And additionally, we need to figure out why the 10 other solutions did not work. It's really odd that we only had one solution out of 10 work. So we even tested those 10 multiple times, and they just never worked for us. So we do need to do a lot of research into that. And finally, enzymatic reactions. So I'll go a little bit lighter here because we didn't really get to perform the larger scale enzymatic reactions. 6 weeks is not a lot of time to be doing a lot of good research, especially on top of the fact that we need to learn the safety protocols and how to use all the machinery and all these theories and stuff. So all you need to know about this part is really we try to use a one-pot multiple enzyme process. So in a one-pot multiple enzyme process, it's just like cooking a stew or something. You take all your ingredients, all your enzymes, everything you want, you throw it in a pot, you kind of let it incubate, and then at the end of the day, you just get your product out. So as you can see, it's really convenient, especially if we want to do it on the industrial scale. So we did some small-scale synthesis in these tiny vials about this big, and we specifically used our LacβNHCbz from our crystallization too, just to see if it was pure enough to run these enzymatic reactions. So these are just some mass spectrometer readings. The high peak indicates that there's a presence of a compound with that molar mass or somewhere near there. So that's the exact molar mass of the HMO we were trying to produce. And ignore the peak size though, because that can be it doesn't actually tell you how much of it is there. Our mass spec's not accurate enough to do that. It just tells you the presence of the compound. But as you can see, we were successful. So there are significant peaks, and our LacβNHC, this tells us it's likely pure enough. However, we still need to, like I said, scale it up to larger sizes. If we want to produce these HMOs for infant formulas, we can't be producing half gram or these tiny amounts. We need to be able to do it in industrial vats. So in conclusion, CBZ tagging seems promising to improve the synthesis, and solution number 3 was extremely effective for crystallization. And finally, the small scale reactions are somewhat promising. However, we need to optimize for crystallization further, and we need to, basically improve the large-scale reactions. Finally, our goals with this is eventually to improve infant formula. With industrial synthesis, we can start adding a lot of these HMOs into infant formulas. Some of them are added 2'-FL, which I think is the most common one, but we want to add as many of them as possible to bring the nutrient or nutrition value of these infant formulas up to standard with the actual breast milk. And additionally, CBZ tagging can be looked into to improve the synthesis of other carbohydrates like glycoproteins. So now I just want to talk about my time at the UC Davis Young Scholars Program. It is a truly amazing program. So it's 6 weeks. The first 2 weeks we have some guest lecturers come in the morning, and then we work in the labs in the afternoon. And some of the guest lecturers were really interesting. There was I think his name was Dr. Kimsey. He talked about forensic entomology. So basically using insects to help solve crimes. He would literally oh, this maggot looks this old, therefore the murder happened at this time. So it's really funny and interesting. It's almost like a real Sherlock Holmes. And Here are just some pictures from our trip. So we got to go to Monterey, so you can see Cannery Row right there. We got to go to the Academy of Sciences in San Francisco, and we got to go underground and see like all their huge specimen library. It's like much longer than this building, maybe even that way. And it's just walls and walls of specimens. And so cool. The food at UC Davis turns out to be really good. This is just like cafeteria food, and like it's amazing. It's by far the best cafeteria food I've ever had. That's me in the lab, and that's me with my roommate, Julia. Yeah, and so here's some more pictures of all the trips we went to. So some 4th of July, and again, we walked over the Golden Gate. So it was a really, really amazing experience. Like, everything about it is amazing. All the students that were there, the counselors were mostly amazing, and then there's also mostly amazing. There's like sometimes, but there's like
honesty.
There was all like the research was like so fun to do, and then like Fridays, and we often have activities, so like karaoke nights, and every Saturday, or we basically got to go on like field trips to places. Like I said, so we went to Tahoe, Monterey, San Francisco, and there's some other ones. One of them, I forgot. And then this is the final picture, at least we took. So some of us woke up really early, like around 5 a.m. to watch the sunrise. It was really emotional because like it was actually such a great experience. If any of you are looking for like a good science summer program, and I've actually talked with them, I'll give you some insider information. You don't necessarily need research experience for this. Like they sometimes want kids without research experience because it makes them like more open to learning than if they've previously done research and they think everything should be done this way. So really consider this program. It has been one of the best experiences in my life. Like if you guys have any students interested, you should definitely recommend it. It's amazing, amazing experience. I cannot stress this enough. And I just wanted to give some acknowledgments. So thank you to Dr. Chen, Yuan Bai, and Zimin Zhang for their amazing mentoring. Could not have done it without them. Thank you to the UC Davis Department of Chemistry and Biosafety for making my research possible. I want to thank Megan and Steven who organized the program, and my counselor, Andrew. And finally, I want to thank Ms. Sarah, Mr. Retta, and Ms. Magania because they wrote both my rec letters and allowed me to do this amazing program. And Ms. Sarah also let me host it here. So, and finally, thank you to all my friends that are here, for showing up. It's like a huge amount of support. Thank you. And then I also need to say thank you to my family because I got COVID in the middle, and they took care of me. Just in general, my family supports me so much. And finally, thank you to all of you here. Do you guys have any questions about the program, or you can about my research? Yes.
How does CBZ affect the health?
Okay. Same.
How does this
So he was asking how the CBZ affects the health benefits of HMO. I think I said it, I might have forgotten though, but we don't actually keep the CBZ on there. I don't think that would be very good. In the end, we can use some hydrogen gas, and we can reduce the CBZ group and just cut it off. It's really simple. So if you looked at my picture back here, that's what some of the balloons were for. They're performing the reduction of the CBZ to remove it. Zed?
So, just curious, in relation to the synthesis that you performed in the lab, how does that compare or differ to the actual creation of HMOs inside the human body?
The enzymatic part is very similar. So in the human body, you basically have a bunch of enzymes. So in this area, and then they basically they'll basically randomly throw on, or sometimes specifically throw on these extra groups that I was talking about, like fucose and sialic acid. And we were basically doing pretty much the same thing. We put a bunch of enzymes into a pot with the precursor, because in the human body, it's always built off of lactose, just like we were doing, and then they assemble it, and then, it gets fed to the baby. Okay, any other questions? Bridget?
How long are the HMOs?
The HMOs can, so generally oligosaccharides, so they'll be around 3 to 10 units in length. But it's a bit of a misnomer because there are oligosaccharides much longer than 10 units in length. And they can be very complex. They don't have to be linear. They can be branched. And there's a bunch of bonding rules. And yeah. Any other questions?